Download this code from codegive.com, link in the description below. OK, let's dive into the fascinating, and often misunderstood, world of adverse yaw, often referred to as the adverse rudder effect. This tutorial will break down the phenomenon, explain its causes, its consequences, and provide a basic simulation example in Python. Understanding adverse yaw, a deep dive. Adverse yaw is an unintended yawing motion of an aircraft in the opposite direction of the intended roll. It's a consequence of using ailerons, or similar control surfaces, to initiate a roll. It's a critical concept in understanding aircraft handling qualities and flight control. 1. The core mechanism, lift and drag differences. The root cause of adverse yaw lies in the differential drag created by the ailerons. Here's the breakdown. Ailerons are control surfaces located on the trailing edge of the wings. They are typically moved differentially to initiate a roll. Rolling right, example: to roll the aircraft to the right, you typically move the right aileron up and the left aileron down. Lift change aileron down, left wing increases the camber of the wing, increasing lift on the left wing. More lift equals wing goes up. Aileron up, right wing decreases the camber of the wing, decreasing lift on the right wing. Less lift equals wing goes down. Drag change, here's the key asterisk. The wing with the increased lift, left wing in our example, also experiences an increase in induced drag. Induced drag is the drag created as a byproduct of lift. The more lift, the more induced drag. Think of it as the wing working harder to generate the lift, and this work creates resistance. The wing with the decreased lift, right wing, experiences a decrease in induced drag. Adverse yaw the wing with the higher drag, left wing, will tend to slow down more than the wing with the lower drag, right wing. This differential drag creates a yawing moment opposite to the direction of the intended roll. So, if you're rolling right, the aircraft initially yaws left. This left yaw is the adverse part because it's against the desired maneuver. 2. Why is it adverse? It's called adverse because it's an undesirable side effect. Ideally, when you command a roll, you want the aircraft to immediately roll in that direction, not yaw the opposite way first. It complicates the coordination of the aircraft in flight, especially during precise maneuvers. 3. Factors influencing adverse yaw aileron deflection the larger the aileron deflections, the greater the lift differential and, therefore, the greater the differential drag and adverse yaw. Aircraft speed adverse yaw is more pronounced at lower speeds. At higher speeds, the aerodynamic forces are greater, and the yawing moment due to adverse yaw is a smaller percentage of the overall forces. Wing designs with higher aspect ratios, long, slender wings, tend to exhibit more pronounced adverse yaw. This is because they generate more induced drag. Aileron design the type of aileron and its integration with the wing affect the drag characteristics. 2. Mitigating adverse yaw. Because adverse yaw affects the handling qualities of the aircraft, several techniques are used to minimize or counteract its effects. 1. Differential ailerons ailerons are linked so that one travels a greater distance up than the other travels down. The upgoing aileron has a smaller drag increase than the downgoing aileron. This helps to balance the drag forces. 2. Frise ailerons these ailerons protrude slightly below the wing surface when deflected upwards. This protrusion increases the drag on the downgoing wing, helping to equalize the drag forces and reduce adverse yaw. 3. Spoilers spoilers are surfaces on the top of the wing that, when deployed, disrupt airflow and reduce lift and increase drag. They can be used in conjunction with ailerons. If a spoiler is raised on one wing to assist with rolling, its primary effect is to add drag to the wing that is rising, thus counteracting adverse yaw. 4 flap ailerons * combine the functions of flaps and ailerons. By linking the movement of the flaps with the ailerons, the drag can be adjusted. 5 rudder coordination * the pilot can use the rudder to counteract the adverse yaw. This is the classical step on the ball technique where the pilot observes a slip indicator, ball, and applies rudder input to keep the aircraft coordinated, no side slip. However, relying solely on the pilot is not ideal, especially in automated flight. 6 yaw dampers, automatic rudder control. These are automatic flight control systems that sense yaw rate and automatically apply rudder input to dampen out unwanted yawing motions, including adverse yaw. They are essential in larger aircraft. 3. A simplified simulation in Python. Let's create a very simplified Python simulation to illustrate the concept of adverse yaw. This is not a full-fledged flight simulator, but it will capture the essential dynamics. Explanation of the code * 1 parameters * We define basic aircraft parameters like wingspan, coefficients related to aileron effectiveness, and inertia. 2 initial conditions * set initial roll and yaw angles / rates to 0. 3 aileron command * a step input for the ailerons is applied between aileron _command _start _time and aileron _command _end _time. 4 lift and drag changes * the code calculates the change in lift and drag on each wing based on the aileron deflections. This is the key part. 5 moments * it calculates the rolling moment, due to the lift difference, and the yawing moment, due to the drag difference. 6 integration * we use Euler integration to update the roll and yaw rates and angles. This is a simple numerical method to approximate the solution to the differential equations of motion. Note that this is a simplification. In a real flight simulator, more sophisticated integration methods, example Runge-Kutta, would be used for better accuracy. 7 plotting * the code plots the roll angle, yaw angle, and aileron command over time. How to run the code and observe adverse yaw *. 1 Install libraries * make sure you have NumPy and Matplotlib installed. You can install them using pip install numpy matplotlib. 2 Run the code * save the code as a Python file, example adverse_yaw.py, and run it from your terminal, python adverse_yaw.py. 3 Observe the plots * look at the yaw angle plot. You should see that when the aileron command is applied, around t=1s, the yaw angle initially goes in the opposite direction to the roll. This is the adverse yaw. The aircraft initially yaws left when trying to roll right. The roll angle should be increasing during the period when the aileron command is applied. Important considerations and extensions *. Simplifications * the simulation is extremely simplified. It omits many important factors, including roll and yaw damping, air resistance that resists rotation. Aerodynamic forces dependent on angle of attack, side slip angle, airspeed. More realistic aerodynamic models. Control system dynamics. Gravity effects. Rudder coordination * You could extend the simulation to include a simple rudder control system that tries to counteract the adverse yaw. This could involve adding a term to the yawing moment that is proportional to the side slip angle, or yaw rate, acting as a yaw damper. Nonlinear effects * The relationships between aileron deflection and lift/drag change are actually nonlinear in reality. Visualizations * For a more intuitive understanding, consider using a 3D visualization library, like Matplotlib.animation or a game engine, to visualize the aircraft's motion. More realistic aerodynamics incorporate more complex aerodynamic models based on airfoil characteristics and wing geometry. In summary, adverse yaw is a crucial concept for understanding aircraft handling. This tutorial has provided a detailed explanation of its causes, methods for mitigation, and a basic simulation to visualize the effect. By understanding these principles, you'll be better equipped to analyze and design flight control systems. Remember that the simulation is a starting point, and more complex models are needed for real-world applications.